All right, today we're going to talk about inverse trigonometric functions, and we're going to start that by doing a little bit of exploration on what we know so far. And so we'll start with these triangles that you learned way back in geometry. And so remember when we were solving for something like x here, we have an angle. We're looking for the opposite side, and we have the hypotenuse. And so we can say the sine of 42 degrees is equal to x over 9. And then we cross multiply, so we get 9 times the sine of 42 degrees is equal to x. And so then we plug that into our calculator in degree mode, since this is in degree, although in AP pre-cal, we usually work in radian mode, so you usually want it in radian mode, but in this case, we would put in our degree, and we would get 6.022. And so that would be our opposite side. Well, in cases when you're looking for the angle, and so this is a similar triangle to where it has an opposite and a hypotenuse from the angle, but we're looking for the angle here. So we would say the sine of x is equal to my opposite over my hypotenuse. Well, now we need to solve for this x. This is all one term, so I can't just separate these. And so we know that if we do the inverse operation, we can get it by itself. And so we can say x is the inverse sine of 3/8. And so we would put that in the calculator. You hit that second sine button, and that's going to get you the inverse sine. And so we would find that x is 22.0 degrees. So that's what we want to focus on, is this inverse operation. It says, as with all functions, the inverse of a trigonometric function is the result of switching the input x and the output y values of the function. As a result, the output value of an inverse trigonometric function will be an angle measure. So in this case, we were solving for a side, and in this case, we were solving for an angle. So that's what it's telling us. When we're using that inverse, we're finding that angle. The proper notation for that is the -1 symbol that we've seen with other inverses this year, but you can also write it as arc sine of x. So both of these mean exactly the same thing, and they are both the notation for an inverse trigonometric function. So in either notation, we can say the arc sine of x when we're reading that out loud. So if we had a statement like this, sine of pi over 6 is equal to 1/2, which we know this is the unit circle, and you should know that really well at this point. So the sine of pi over 6 is equal to 1/2. If I wanted to write an equivalent one using the arc sine notation, I would say the arc sine of 1/2 is equal to pi over 6. So the arc sine is looking for an angle. The regular sine is looking for that side. All right, so we've talked about evaluating from the unit circle. So sine of 7 pi over 6, we know this really well at this point. You should know that's -1/2. And the sine of -pi over 6, which is coterminal with 11 pi over 6, we know that's -1/2. The sine of 11 pi over 6, we just said these two are coterminal, so we know that is -1/2. And the sine of 19 pi over 6, that's 3 times 3 and 1/6 pi. And so 1, 2, 3 pi's, and then another 6 of a pi would again give me -1/2 for the sine value. So we get -1/2 for a lot of the different terms there. So we're going to look at that here. If we plotted the ordered pairs from that first question, well, -1/2 is found right here. This was one of our points. That's our -pi over 6. And then we've got another one right here. Another one right there. And another one right there. So how many solutions are there to sine of theta equals -1/2? Well, there's an infinite number of solutions. We know this is periodic, and so it is going to continue over and over again. So we would have an infinite number of angles that would give us a value of 1/2. And so when we say is sine 1 to 1, we know the answer to that is no, it's not. It fails the horizontal line test. If I dropped a horizontal line right here, it would touch in more than one place. So it fails the horizontal line test, which tells us that the inverse is not a function, given that there's an infinite number of solutions. Now, if we restrict the domain, then we are going to be able to get it to be one-to-one. So let's look at this and see what our longest interval is that we can do without it repeating. And so that would be this portion right here. If I use just this portion, it is going to be one-to-one. So we can restrict the domain to negative pi over 2 to pi over 2. All right. The next part here shows us a cosine graph, and it wants to see, is that the same restriction that we would have for the cosine? But from negative pi over 2 to pi over 2, we have these values right here, which would fail our horizontal line test. So no, we would not have the same restriction for the cosine one. For our cosine one, this is the longest interval that will pass that horizontal line test and make it one-to-one. And so in that case, our restricted domain would be from 0 to pi. Now the tangent one, that one's kind of the easiest to make it one-to-one because this increases like this between our two vertical asymptotes. And so from one vertical asymptote to the next would make it one-to-one. And so that again is negative pi over 2 to pi over 2. All right, now that we explored that a little bit, let's dive a little bit deeper into these inverses. So right here, we have our sine graph. The domain for the sine graph is from negative infinity to infinity. And the range is from negative 1 to 1 as we look at this graph. And so we see that it starts right here. It is periodic. It will repeat this way. It will repeat this way. It does fail the horizontal line test. And so we talked about restricting that domain. So now we're going to look at that inverse. And so for that inverse, we said in this case, if we actually graphed it, let's take some points and see what that would look like. So my first point here, pi over 2, 1. I'm going to take this point right here. Actually, my easiest point is 0, 0, so I'll graph that one real fast. 0, 0. Now, when we do an inverse, we said we change our x and our y values. So this would become 1 and pi over 2. So I go 1 and pi over 2. The next point here would be pi 0. That's this point. And so when I change that for the inverse, it becomes 0 pi. And I get that point. As I continue to flip these points, switch my x and my y values, I end up with a graph that looks like this. It fails that vertical line test. Each input value does not have exactly one output value, which is what we need for our one-to-one function. In this case, the domain is from negative 1 to 1, and the range is from negative infinity to infinity because we switched. Sorry about that. I put brackets there instead of parentheses. There we go. Negative infinity to infinity. And so when we switch our x and y values, that's switching our domain and range. So our domain here became the range, and our range here became the domain. And so we get this graph. We said that one doesn't work. So we switched our x and our y values to get the inverse. But this here is not a function. Each input value does not have exactly one output value. So we need to restrict our domain and focus only on the principal values. On our exploration, we found those values were from negative pi over 2 to pi over 2. This portion of the graph. It is where it does not repeat. Each input has one output. And so that becomes our range here. And our domain is at negative 1 to 1. So if we think about that graph now, it looks like this. So that is going to be our inverse sine function. Because trig functions are periodic, we must restrict their domains to create their corresponding inverse function. So this is our inverse function with that restricted domain of negative pi over 2 to pi over 2. In order to make the inverse a function, we will restrict it, again, negative pi over 2 to pi over 2, as highlighted in the figure above, and we look at this point right here. If you think about that on the unit circle, pi over 2 is right here, negative pi over 2 is right here, so we are only talking about those angles in the first and fourth quadrant. We would not use any in the second or third quadrant. All right, let's look at our cosine graph now. In this case, it is graphed right here. We said the domain is from negative infinity to infinity, and the range is negative 1 to 1. This graph also fails the horizontal line test, so our function is not 1 to 1, but we would go ahead and graph this part here. So we're going to take some points. My first point here is 0, 1. So 1, 0, I've got a point. My next point, negative pi over 2 and 0. That's this one right here. So 0, negative pi over 2 is that point right there. And then we'll do the same thing for this side right here. We've got pi over 2 and 0. So 0 pi over 2 is right here. And then we keep going. And so we get a graph similar to that sine one that looks like this. This is not a function. Our range would be from negative infinity to infinity, and our domain would be negative 1 to 1 because we switch the x and y values, so our domain and range switch. In order to create one that is a function, we go ahead and restrict that domain. And so our longest portion right here that passes that horizontal line test that's 1 to 1 is going to be this portion right here. And so that is from 0 to pi. And so our range is going to be from 0 to pi, and our domain is going to be from negative 1 to 1. Now this will be a function. I graph those points here. And so there are my values from 0 to pi. Again, 0's at 1, so we get that point 1, 0. Pi over 2, 0, so 0 pi over 2. And then pi is negative 1, so negative 1 pi. That's where I'm getting these values right here. So this is going to be my inverse cosine graph. So again, here on our notes, we're going to go ahead and state that the graph of cosine of x will be restricted to 0 to pi to make it a 1 to 1 function. So we're looking at these values here. If we looked at that on the unit circle, 0, pi over 2, and pi. So we're talking about this first and second quadrant. We would do nothing with the third and fourth. All right, for the tangent function, we said that's going to be the easiest because it's from asymptote to asymptote. So we restrict that domain to negative pi over 2 to pi over 2 because that's where my two vertical asymptotes are, and that makes it 1 to 1. So important note about the inverse trig functions, it's important to always remember and consider that domain restriction as we work on solving and finding the inverses. Those are really important. You're going to, again, on sine of x, this is pi over 2, this is negative pi over 2. We would never want to give anything in these two quadrants, only these two right here. For the cosine of x, it's from 0 to pi, so we've got first and second quadrant, and tangent of x, again, is negative pi over 2 to pi over 2, so we're looking at the first quadrant and the fourth quadrant. So when we evaluate these inverse sine functions, and inverse cosine and tangent, we keep this in mind. So it tells us the cosine, the arc cosine of negative square root of 2 over 2. And so cosine is going to be the easiest one since it uses the first and second quadrant. We know that the negative root 2 over 2 is the one that falls right here. We're working backwards. This is where you have to know that unit circle really well. And so we know that angle is 3 pi over 4. And so that's what we're looking for there, the angle that would give me this ratio. So for sine, that's the y value on the unit circle. And so our y value is negative root 3 over 2. Now, in the restricted domain, that means it would be in this fourth quadrant because sine is positive up here and negative down here. And so negative root 3 over 2, we have a y value of root 3 over 2 on the one with the 3's in the denominator. And so it would be a positive pi over 3 this way and a negative pi over 3 to get it into the fourth quadrant. All right, for our inverse tangent, now we really have to work backwards and think through this. We know tangent is y over x. So when it gives us something like root 3, we know that's root 3 over 1. And so that had to come from the point where my y value had the root 3 over 2. And the x value had the 1/2. And so we're looking for this value. That's going to be, again, the one with the denominator of a 3. It is in the first quadrant because it's positive, so it would be pi over 3. If it was negative, it would be in this fourth quadrant, so it would be negative pi over 3. All right, before we finish this intro into the inverse functions, we're going to go ahead and talk about what a test question could look like on this. And so here we have an MCQ one, and it says the angle theta is in standard position. The terminal ray intersects the unit circle at point P. And so that's this one right here, whose coordinates are x and y. The points Q, R, and S are the result of the terminal ray being reflected over the y-axis, the origin, and the x-axis respectively. For each of the following expressions, determine which labeled point intersects the terminal ray at the given angles. And so right here it says the arc cosine of x, well, that would be point P, right here, where that x value is right there. That's where we're going to find our cosine. And so then our sine inverse, arc sine, of negative y. And so negative y would be this point right here. So we would find S there. For our cosine, our arc cosine of negative x, that would be this one right here of Q because it reflects over the y-axis. We know that the arc cosine happens in these right here. And then when we're talking about the tangent inverse of negative y over x, we know that one's going to be S because the arc tangent only would work with these two, the arc sine would only work with these two, and the arc cosine would work with these two. So for this one, it would be S. So make sure that you're thinking about those domain restrictions when you are applying the answers to these. All right, that's the end of our intro to the inverse trig functions. I will continue. Watch that next video for the rest of it.